Since I won't be starting a master dissertation until May, I'll be giving you the work of the graduate dissertation I did on a subject I enjoyed very, very much, and it was really fun to do research into and to find out more. Because swinging on a playground swing is basically something that every 2-year-old figures out within about half an hour of sitting on it. He figures out how it works. But then we looked at it again and sort of tried to, from an engineering point of view, look at it, and we're like, how does this actually work? And we realized that when coming up with this sort of, can we figure out how it works, then can we get to the question that every kid is dreaming of. Can you actually go around on it? Can the thing make a full rotation? And if so, how would you then achieve it? So this led to a lot of enthusiasm, and quite quickly we got the answer to one of our questions, and that's demonstrated in this video. This is a sport in Eastern Europe. It's called kicking, and as this person will demonstrate in the next swing. It is possible to make a full rotation. So we then started out knowing this, that it is possible. We then started to look at it, how does that then actually work? And to make it feasible to work on within the time we had, we decided to look at the standing swinging on a rigid swing. So with a rope swing, I have to disappoint some people, it's not possible, because once you get above the horizontal you will drop down, literally, so you can't get the speed up, so you need a rigid swing, a bar swing, and we looked at the standing motion of the swing. So, as a kid, you've done it, you've stood on the swing and moved up and down, because if you're doing it in a sitting motion, there's 5 points of view that are moving around, and that would have added a lot of complexity to it, and I'll get to that later. And we've assumed a point mass, so that means your whole body mass is a point, and the movement as you're standing up and sitting down is a sinusoid. And to demonstrate the movement of the swing, this is where you start off in a sitting position, then you go down, in the bottom you stand up, then you swing up, and then you sit down again, and that brings you back to point 1. And we've also made a starting angle of 45 degrees, basically your dad giving you a push. And this led to this lovely figure with all the variables. I won't go into this, as Chris said, we should stay away from equations, which I'll try to do as well. But this is sort of all the variables that you have in that motion. So then the research we tried to do is we looked at the movement of swinging, and then especially we looked at what's the best way of swinging. Because a kid knows that he has to move his legs and body at some point, but if you then try to put that into mechanics, what's the most efficient movement in rotating as quickly as possible? And we did this by looking at the what we call TA and TB, and this is the normal situation. And we've looked at an extended TB, which TB is the time required to stand up and sit down. So it's sort of how quickly you do that motion. And the TA is the offset from the bottom point and the top point of the motion. So sort of how big the offset is where you start your movement. How we then did it, well, this led to this lovely equation, which I won't go into, but it's a lovely second order differential equation, which was a pain to work with. We've then put that in a numerical model in MATLAB. Widely used engineering tool to be able to simulate this in a numerical way, and we could quickly change variables, quickly change what we, where we wanted it to, and it's really good to work with. You can get the output in any way you want it. But then to make sure that the MATLAB model was right, and you can make a MATLAB model out of anything basically, it doesn't necessarily mean it's right. To then be able to validate this model, what we did, we made a scale model of a swing. I haven't got it with me, unfortunately, but it's about that high it was, and it's able to swing autonomously. It was driven by microchip and with a small brass weight that was on a servo motor, you could simulate the movement of the person standing up and sitting down. And we built the model next to MATLAB, and we'll get to it later with it validated MATLAB. So if you then look at what this is the output from the MATLAB, so we did simulations on the variations of TA and TB, and as you can quite clearly see, with there are some variations which we'll briefly touch on. As the TA increases, so your offset from what you should be doing increases, the time it requires to get to pi, what we call the time to get to the vertical, increases. And the same for TB, so sort of the slower the movement is, and the less power you exert in the movement because you're doing it slower, the longer that takes as well. Except for what we came across, and we couldn't get it out of our simulations, is this bit here. We always came across this point where at some point it became quicker again, and we were looking into this, how is this possible? And then we did the simulation, and it looked like this. Here you can see the two different movements with different TBs, and you can see the motions, and at some point they'll both reach what we've called T pi. But here on the left you can see they almost being there, then moving up, and on the right it's already there, and then making a swing. But because your motion is in the very non-linear area of motion, it takes a very long time to get up, get out of the equilibrium and fall back. So there was always a point where this would happen and this occurrence would take place, and it would take longer, even though sort of your theory would be that it would take smaller. Have we got sound on or not?
Yeah.
Can you turn off because it'll be very loud. So we then make the model and make a video of it. And my project partner behind it. You can see the small weight moving up and down. And there it goes. And this is the model we've used, and when we made our MATLAB model, we gave it the exact same set of variables as this one. This is the graph we got from it, and here you can see the motion as simulated by the MATLAB, and here on the right you can see the motion with our scale model with a number of number of repetitions, and this sort of proved the MATLAB model. We validated the MATLAB model through this, and we could therefore then do the other experiments we want to do with the quick and easy variations that are possible within MATLAB, but the fundamentals of the MATLAB model were correct sort of with a real world model. So through that validation, we were then able to get the models previously shown, and that led to the conclusion of the research, which was that the hypothesis that we had, that as a kid, if you do it as well timed and as quickly as possible, you will actually get there as soon as possible. That was confirmed. The shorter you have your time of motion, so the quicker you able to stand up or sit down, the faster you will get the full rotation, and the better you're able to time it at the exact bottom of the pendulum motion and the exact top, the better you get at achieving that full rotation quickly. We then looked at, we've now looked at a very small part of this. We've proven partially that what the governing motion is behind it. But there's a lot more to it. We found out, even though any 2-year-old can do it, there's a lot more to it that can be researched. And especially the starting motion of the swing and the sitting motion on swing. So as child sitting down. We weren't able to go there because that would mean if you're sitting on the swing, you're moving your legs up, your body down, and your head down, and that would add about 5 points. 5 point masses on the point mass on the one, compared to the 1 point mass we have now. So that would be sort of an extra simulation you would need to do of the body on that swing. So that was one thing our professor wanted to take forward in the research and have someone actually look at a real kid on the swing, not just one standing up. And that leads me to the end of the presentation. Thank you.
Thank you, Matthew. John?
If you start modelling this with someone sitting down and adding in extra parameters, won't you then be very sensitive to initial conditions? So if you do a simulation, you're going to get like chaotic motion, aren't you? So if you simulate it, you'll probably see more of these effects where you've got the two slight differences. But I'm not sure you'd be able to recapitulate them in a toy model as well as you've done here, because like small changes at the start, you won't be able to. So is that the planning of doing more things? You're going to continue like simulation and building a model, or you're just going to go forward with the simulation?
Well, I've left that university now, so I'm not going to be able to continue this work. So, but our professor was very interested in continuing it because it became part of the dynamics lectures afterwards, because it's such a sort of a simple thing, everyone can get their heads around it, and he wanted to take it further because it's sort of adding complexity onto something very simple. The pendulum motion is basically the most simple motion in dynamics, so this adds to it. Small steps. You basically go to a compound pendulum, and then a 5-foot compound pendulum.
Yeah.
Once you've added the whole body.
Except those messes are controlled.
Sorry?
Yes,
they're controlled well.
Yeah. Any other?
The experimental data seem to have a lot of variances towards the end of the experiments. I was wondering what some of the, it was the same model, right? So I was wondering what some of the factors that contributed to variance might be.
Variance we had was the air resistance, because the model was bigger, because we had to make it rigid enough. It was bigger than it'd be in the real world, so it had quite a lot of air resistance, and it kept on moving through the same air every time, so you basically created a wind in one direction and then started moving back through it, and because that movement is in the nonlinear parts of the motion. So as you saw in the abnormality that occurred in the MATLAB model, once you sort of get motions very high up, that greatly can really shift the time, and that's what's happening in that on the far right in that graph. You're moving in those areas because you're moving slower in your top position, so you're moving, you're changing very slowly in the very non-linear region, so you get much more variation.
Also on that same plot on the far left, you had a bit of a discrepancy between your experimental results and your predicted ones.
Yep.
About sort of 15%.
Yep, that was the air friction we found out. Because
okay.
we were able to model that to a degree in MATLAB.
Yeah.
But it was the way we build it, we were physically constrained by what we could build the swing out of. Because it had to be.
But you sort of ascertained that discrepancy, because it was greater than your error bars, that would have been accounted for by the system.
Yeah.
Yeah. Okay. One last question before we let you sit down. That small dip in the result,
yep.
Did you try increasing the resolution of calculating some of the TA and TB values?
What do you mean?
Well, you had that small dip, so my thinking would be you reduce the value of the resolution of TA and TB to see if that sort of persists, or whether it's a numerical sort of cut.
No, the dip kept on coming back. So there will always be these points where you needed one more swing to build up the energy. You've got the energy building up, and basically you build up energy, but because you're standing up, you're losing a bit of energy, and then you're standing up, so you build up a bit of potential energy, and then you're sitting down, you lose a bit of potential energy. There's a continuous sort of a graph that goes like this. If you depends on how you plot it, but it builds up energy continuously.
Yeah.
And then always in one of those, it just wouldn't have enough energy to make it all the way around.
Yeah.
So it
Right,
kept on coming.
so the termination condition is actually a sort of stepped function.
Yeah, it's sort of a step function.
Very good. Cool. Thank you. Right. Our next speaker.